hear me?
Yes, but can you please switch cameras?
It hasn't started yet.
I see you now.
You see me attaching the microphone? Oh, can you hear me now?
Yes, we can.
Great, thank you. All right, so welcome to Lecture 3. It's a crash course on Infinity 1 or Infinity N categories. We'll see how far we get. So, what was the last thing we did yesterday? We had our first definition of an Infinity 1 category. An Infinity 1 category is a category enriched in spaces. Okay, so this was our first definition of an Infinity 1 category. There will be at least 2 more today. And then we'll talk about why we can make different definitions and be happy about it. So what do I mean, first of all, by spaces? We already had a little bit of a discussion about this yesterday. So for us, this can either be top. By top, I will restrict myself to nice topological spaces, namely compactly generated Hausdorff spaces. And the reason for choosing those is that alternatively, we also want to be able to take simplicial sets. And, well, if you look at the model categories or infinity categories of top and simplicial sets, those are equivalent. So this direction is just given by taking the singular simplicial set of a topological space. The other direction is geometric relation. But yeah, so general topological spaces are a little bit ill-behaved, so we want to be able to deal better with them. Okay, so let's look at examples. So, well, top or simplicial sets themselves. Okay. So between any 2 topological spaces, if we're in this assumption, compactly generated Hausdorff, we look at continuous maps between them, we actually have a nice topology on them, compact open topology. And simplicial sets, it's also very easy to, well, the morphisms of simplicial sets are just, well, level-wise. And then this is actually the zero simplicities of a simplicial set themselves. And the second example, for those of you who know what that is any nice, and by nice usually we already ask for simplicial, model category. So yeah, this is a bit tautological. A simplicial model category is one which is enriched in simplicial sets. So it's a bit tautological, but I wanted to have this on the board because most of the model categories that you encounter actually are sufficiently nice. So simplicial And actually, there's another word that I would like to add, combinatorial. And the reason is that if I take a combinatorial simplicial model category, if I look at those guys, you should really think of these as being a presentation of an infinity one category. So Lurie made this a lot more precise, actually. So conversely, if you have an infinity one category, by which he doesn't mean exactly that, but we'll get to that later. But if you take any infinity one category, which is presentable, then you can realize it in this way. So you should really think of this as a presentability statement. And our third example, which will be our main example, are cobordisms. Okay. All right, so now I will spend some time telling you how to make cobordisms into such a thing, because this will be the thing that we will use kind of going on. For this, the main tool will be what's called Whitney's embedding theorem, which you may or may not have heard of. Am I writing big enough? A little bit more? Good. So Whitney's embedding theorem tells us that any smooth n-dimensional manifold can be smoothly embedded in some big R. So I could even write here 2n, but I don't want to be so precise. I'll just write R infinity, which is just the co-limit over all RKs. Well, RK is in RK plus 1 just by inclusion of the first coordinates. And so this will be the basic thing that we need, a basic tool. Which color was good yesterday? Red? Yeah. Yes, I saw them. So we can also vary this, actually. So, I mean, we'll want to have bordisms. Bordisms aren't just manifolds, they're manifolds with boundary. So there's a version with boundary. And then we replace this here by R greater or equal to 0 times R infinity. And we have more colors today. We will want manifolds with corners. And then, well, we also have a version here. And of course, what I mean by this is, I mean, if they're embedded here, then the boundary of my manifold will be sent to the boundary here. I hope that's clear. Okay, but there are two, we need even more, actually. So this can actually be modified for bordisms. So then what we get is actually we get, they're embedded into 0, 1 cross R infinity, such that really over 0 we have the incoming and over 1 we have the outgoing. So that's how we picture them, how we always draw them. Or even bordisms of bordisms and so on. And then we have that they can be embedded into 0, 1 to the k times r infinity. So yeah, I should start listing some references. So I learned these things about manifolds with corners and embedding them in a nice paper by Gerd Laures. And also this embedding of the Bordisms. This embedding of the Bordisms of Bordisms, I did not find a reference, so we proved it in a paper. But if somebody knows of an extra reference, please let me know. This was not that difficult, so probably it appeared somewhere else as well. And the final thing that we need for our Bordisms, because we will want to be able to embed them, but if I choose now an embedding, you might say, well, but this is a choice, this is extra data. This was not there in the original Bordism category. So why can I choose these embeddings? Well, the space of such embeddings is contractible. So, I mean, this was already in Whitneys, an extension of Whitney's theorem, but then also their version for the boundaries and so on. So that means, okay, we're putting extra data there, but if I just look at the space of this extra data, then that's contractible. Any questions at this point? Actually, I have space here. All right, so now let me tell you what 3 is, or a version of 3. We will see other versions later. So I will now call this Ncop, now with a curly C. And the ideas of this, as far as I know, go back to work by Ulrike Tillmann and Ib Madsen. And the version that I'm going to present here is in a paper, beautiful paper, the GMTW paper, where the M and the T are the ones from before, and the G is Søren, and I don't know how to pronounce his last name. Latius? Okay. Because you hear many variations thereof, and I'm Copenhagen, so I should know. And Michael Weiss. So this is a very local thing. So what are objects in this category? The objects will be pairs, M a manifold, and A a number. So A is a real number, and M is now a closed n-1 dimensional submanifold of some big R infinity. Okay. So let's draw a picture. Here I have my R, here I have my A, and then here I will have my R infinity. And now, well, this might look something like this. Okay. So I'm just putting something in a slice here. And what are morphisms? So a non-identity morphism from M0 with A0 to M1 with A1 is a triple now, W, A0, A1. So those are the A0 and A1. And here, and now A0 should be less than A1 in R. And W is a compact submanifold in A0, A1 cross R infinity. So if I extend my picture from before, then I have my A0 somewhere, my A1 somewhere, and then I have something sitting over that. But this is not quite enough. So I drew this suggestively, and not quite right, actually. So we will want extra conditions. Okay, so the extra conditions will be about here and here. And this should remind you of the colorings that we had in defining boardisms. So I will have to switch the board now. So for those of you who are viewing, is it okay, I hope, if I switch? So what are our conditions? So the first condition is, well, the boundary of W. This W is a manifold with boundary, but the boundary should really only be over A0 and A1. Okay. And the two others are the ones that I kind of tried to draw a little bit in red. So if I intersect W with, so there exists an epsilon greater 0, such that W intersected with A1 minus epsilon to A1 cross R infinity. This is just, and it is on the nose, this interval cross my source. Sorry, I wrote the wrong one. Wrong line. The source is A0, of course. And now I have the other condition. I should have just switched 0 and 1. That would have been a lot easier. So we're asking here at these boundaries that there's a little neighborhood around this where it's just a cylinder. Okay. And that's nice because it actually makes us able to compose on the nose. So this fixes the thing that we discussed. So in the boardism category, the way we saw it yesterday, we had collars, and those allowed us to compose, glue the things. Now here, well, if we have cylinders, then of course I can just glue them together, I get something smooth. But this can also be modified. So, I mean, there are many variations of the coboardism category in the literature where exactly precisely you want to modify this a little bit. And we will see variations of that. Just for our purposes, it turned out to be more useful to have something else. Yeah. Okay, but we want the topological category, not just the category. And so the topology that we will take is the following. So if I take a manifold, so this will be one of my objects, M. I always denoted them by M. And these are definitions of manifolds of R infinity. So, well, I can look at embeddings of M into R infinity. So just to be precise, what I mean by this, I just take embeddings of M into some Rk and the colimit for those. And now I can endow this thing with the Whitney topology. Okay, but we want submanifolds. We don't want embeddings. So how do I get submanifolds? Well, I can act on this thing by diffeomorphisms of M, just by precomposing. And, well, I can form a quotient. I call this B infinity of M. And this will be a principal diff M bundle. And this action here is free. So if we go back to Whitney's embedding theorem, the last point that I made was that the space of embeddings is contractible. So this is contractible. So that means that this B infinity of M is a model for the classifying space of diffeomorphisms of M. And this is what we will want to use to topologize. So the objects of this N curly cob, well, they're just R cross disjoint union over diffeomorphism classes of M of this B infinity of M. And if you stare at this, you will see that, well, the underlying set is exactly the objects. And for morphisms, we do the same. So we take this half space just as a subspace of R2. And then we have, again, B infinity of W. So I don't want to repeat the whole story now for cobordisms. It's pretty much the same. So this is now a diffeomorphism class of abstract bordisms. By abstract, I mean how we defined them yesterday. and we defined diffeomorphisms yesterday. So this is actually W theta 0, theta 1, and if you wish the P, right? So these collars. And when I talk about embeddings or diffeomorphisms, we always, with diffeomorphisms yesterday, we had this condition that the collars have to be sent to each other. Of course, with embeddings, it's the same. Okay. So this thing here are embeddings of W into 0, 1 cross R infinity. And these embeddings should respect collars for some epsilon greater 0. So this epsilon greater 0 gives me a collar here, right? Okay. Oh, yes, thank you. Right, but I said before those are the non-identity morphisms. So what about identity morphisms? So in this picture, they're just formally put in, just taking a disjoint union. So for the purposes of the paper, this really didn't matter. It didn't really matter how the objects were put in. But honestly, I would not want that because if I take a coordinate of positive length and then I take the following path in the space of morphisms, I just shrink the length, I would actually want that to eventually end up being an identity. But that's not the case in this morphism space. Right? This morphism space, I can't do that. I can't shrink the length to 0. So for the purposes of what was done in this paper, namely computing the classifying space, this really didn't matter at all. But for the purposes of having a nice cobordism category, that's certainly a property I would like to have. Okay. Here. Yes, but I don't want a disjoint union here. Ah, I see. Yes, that was going to be my next point. So this is not a category, as Natalie is pointing out, this is not a category enriched in spaces. This is what we would call a category internal to spaces. So internal just means that we also have a space of objects. It's still an infinity 1 category. Because it was actually shown that categories internal to spaces are also a model for infinity 1 categories. That was proven by Geoffroy Horel in a nice, very readable paper. But I still wanted to give you this as an example because it was certainly one of the motivating examples for this whole story. I could also forget the topology, yes. But I mean, that's even weirder, right? Because then I have like the same manifold twice. So, I mean, the morphisms know about that, yes, exactly. So that's why I'm saying, I mean, that's partially a point of taste, or depending on what you want to do with it, that's okay or it's not okay. Yeah. So as Natalie's pointing out, if we just take the discrete topology here, well, then we have two objects which are different, but are like represent the same thing in the abstract cobordism category, but there is an isomorphism between them, namely just given by the cylinder. Okay, so we have too many objects, but we also have extra isomorphism. So the categories will still be equivalent. So it's still okay in that sense. Yes?
Internal to spaces is something better than enriched. It's stronger.
It's stronger. I'm not sure I would say better.
No, better is the wrong word, but I was confused when you wrote it's not enriched in spaces rather it's internal. You could forget to, that's what this is saying. Right, so from internal you can forget to enrich. Right.
Yes. So you can forget the topology on objects, and then you get something enriched in spaces. That's absolutely true.
And the infinity category you are talking here is coming from this paper that you said?
Yes, this topologically enriched category I literally took from the paper. Yeah. So, the reason I'm pointing these things out is that there are many choices that we can start making here. And as long as they're equivalent, I'm free to do these choices, and depending on what I want to do in practice, one of them might be better than another. So when I said, well, I find it a bit frustrating that we have a disjoint union here, well, that's maybe actually something that really is an argument, but on the objects, whether we forget the topology here or not, we will get equivalent categories. Okay, so the other remark I wanted to make is the one about the cylindricity that I implicitly already mentioned. So, of course, I didn't tell you how to compose, but hopefully that's not so hard to see. It's exactly the same, just gluing of cobordisms. And our problem with composing, or it wasn't a problem, right? We had fixed it by taking diffeomorphism classes or by fixing collars. And now here in this version, we also have collars that are fixed, so composition is not a problem. But if you start with a cobordism, like finding an embedding such that it really is a cylindrical thing might not be that easy. Or for various purposes, also already in that paper, this condition of cylindrical is relaxed a little bit. And that's also something we will see in the infinity n category. Yeah?
Are you identifying translates because all morphisms are going left to right? So how are you getting isomorphisms? Because once you compose, you're not going to go to the same coordinate path, right?
Sorry, can you say that again?
Are you identifying across the R, like?
No.
But then there are no only isomorphisms are identity. Am I right in?
Because you're saying otherwise we don't have the identity on the nose, but just... Yes. Yes, that is correct, yeah. So that's one of the reasons why adding a disjoint union with the objects here is not satisfactory in that sense. Because we certainly would want an actual honest cylinder to be, well, there should be a path in this topological space to the identity, which there is not. Yeah, exactly. So as I said, for the purposes of that paper, this works perfectly fine. It actually doesn't matter what you put here. But if we actually want to talk about the cobordism category as a category and not take the classifying space, it does make a difference. Yeah. Okay. Any other questions at this point? Okay, so we'll revisit the bordism category in a different version later. But now I would like to continue with the next model of infinity one categories. And the next one is the probably most prominent one. It's quasi-categories, which also are called weak Kahn complexes, or Jacob Luria, and nowadays many people just call them infinity categories. So I'm in this course on purpose not using this word because we'll be also talking about infinity K categories. So here, I mean, the one is not implicitly there. And I mean, I would not use that other terminology anyway, but there actually is a part of the Australian community who says infinity category for a thing that has K morphisms for all K, which are not invertible in general. But of course, I mean, in many texts nowadays, this is just used synonymously for quasi-category. And I mean, certainly that's good practice to use that. It's just as soon as there's also some infinity K around, I find it sometimes can be confusing. So what is that? It is a splitable set X with certain horn lifting properties for what's called inner horns. So there are many words that are new. So the lowest condition is taking 0, 1, 2 inside the simplex, 2 simplex. This is delta 2, and this is the 2 horn, well, the first horn sitting inside delta 2. And my condition says that if I have such an inner horn, so if I have a map to X, then there exists a lift. And I want to stress that this is not necessarily unique. Okay. So why this condition? Well, what is a map like this? So we can unravel this. And now if I just look at this guy, what if I just map 0, 1 to X? Well, I just have something in X1. Or if I take this arrow and map it to X, I just have something in X1, and they must agree over X0. Okay. And so on the other side, if I map delta 2 to X, I just have X2. And so what we're saying is this map here, and you can think of this as being, this is the space of composable arrows plus composition, and here I just have a space of composable arrows. And so, I mean, if I want to compose, I actually want to map the other way. I don't have that really, but I mean, you can think of this existence of a lift as something going the other way, but we're not choosing a lift, right? So this map does not exist because we're not choosing a lift, but that's how you should think of it. But the fact is that the fibers of this map, that can be proven from the rest of the conditions. The fibers of this map, these are spaces, and they are contractible. So we have a contractible, given a pair of composable morphisms, I have a contractible space of possible compositions. Okay. So something that's been implicitly using, maybe I should have stressed that before, is that x0 you should think of the objects, and x1 you should think of the morphisms. So now here in this fiber product, I really have morphism, morphism, and this says that the source of one is the target of the other.
I'm sorry.
Yeah.
When you say that the space is contractible, isn't X2 a set, not a space? What do you mean by contractible here?
You can actually show that that's a space. I'm not going to do that, but one can show that that's actually a space, and as such, it's contractible. Yeah. So right. So I shouldn't have written it that weakly. Yeah. Good point. So yeah. So this is right. What are the more general conditions? Well, now we also have horns in delta n. So what's this? This is the union of I not equals to k of the faces. Okay, so this is the boundary of delta n, but without the kth face. And now we have horn lifting conditions for those, for k not equal to 0 or n. So that's the general form of the condition. Right. So what are examples? Maybe I want to use a new board. So we won't actually use this model much in the rest of the class, but since this is by far the most common one, I can't give a crash course on infinity categories without talking about this. And it's incredibly useful if you actually want to do category theory. So that's why it will actually implicitly reappear and be really necessary for what we do. We will see we need co-limits and con-extensions in a few days for factorization homology. So we certainly need the tools that quasi-categories give us, quasi-categories as a model for infinity categories give us. And thankfully, there were very clever people who did it for us. What are some examples? So the first one is just the nerve of the category. That will be an exercise. And the second one is the singular simplicial set. And this actually satisfies lifting for all horns. So this is the con complex. And yeah. Co-limits, con-extensions, over categories. We have equivalence theorem for detecting weak equivalences. and so on. So, I mean, this is incredibly useful. And, well, I probably don't have to tell you, but most of this is due to, well, first Joyal worked a lot on things, and then Jacob Lurie, of course, wrote the Bible, Higher Topos Theory. Which is great, because now we can just use it. All right, so let's come to our final example. How am I doing in time? Are there any questions at this point? So maybe you all knew this already, I don't know. An infinity one category. We will now try to generalize the condition that we just had before for lifting the inner two-horn. So I wrote that out explicitly before as a map from x2 to x1 plus x1 over x0. And we will generalize this condition now in a slightly different way. So an infinity one category is a complete Siegel space. And this notion is due to Charles Resk. So what is this? That is, it is a simplicial space so before we have a simplicial set with some conditions, now we have a simplicial space. And by space, what I will actually implicitly mean is complex. And we have two conditions. So the first one is the Siegel condition. So for all n greater or equal to 1, we have a similar map to the one we had before from x2, but now we start from xn. And we land in the fiber product of x1s over x0s. And now we're dealing with spaces. So the correct fiber product now is a homotopy fiber product. So I will keep the H here. But actually, if I look here, what I really want here is I want the infinity category of spaces. We have defined what infinity category is, but let's say we have. And then what we really want here is we just want the correct pullback in this infinity category. Okay. So if that's all too complicated for you, just remember this is the homotopy fiber product. And if they're concomplexes, they're fairly explicit models for that. You can just write them down. But really remember, the reason we have the H here is because we are actually working in the infinity category spaces. Yeah? So the question is, if I write complexes, we're working in a model category. The question was, can't we just remove the homotopy fiber product? And the answer is no, because for this we need that the maps, the source and the targets here are fibrations. So actually, if you look at Resk's original paper, he does not have the fiber product because he adds an extra condition. So a reformulation of this, if you know what this means, is level was fibrant. Okay, so that's projectively fibrant. Resk's original model, he actually has projectively fibrant. So you have really fibrant. And then a consequence is that these maps are fibrations, and then you can remove the H. But I think just won't be inductively fibrant. So we're using this modification of Resk's original definition. Okay, but back to Earth, what's this map? This map comes from the maps from 1 to n, sending 0, 1 to I minus 1 and I. So I have n such maps, and then they actually assemble into this. And what's the second condition? The second condition is completeness. And I won't dwell much on this. Feel free to ask me in more details in the breaks or in the exercises. I will write down the condition just so that you have seen it, but I won't dwell too much on that. So the informal formulation is that x0 encodes the underlying infinity groupoid. So if I have a category, I can form an underlying groupoid just by discarding non-invertible morphisms. And I should be able to do the same for infinity 1 category. Just discard the non-invertible 1 morphisms, I'm left with an infinity 0 category, or infinity groupoid. And we saw yesterday that infinity groupoids are supposed to be spaces. And that space is supposed to be x0. Okay. Those were a lot of words for saying that. Yeah, thank you. Yes, the condition was missing. It's not just a map. This is supposed to be equivalent. Thank you. And for those of you who know what that means, recall yesterday we had the following nice one category, namely the walking isomorphism, which just has two objects and one isomorphism between them. And so completeness can be reformulated in saying, well, my x0 is the derived mapping space from 0 to x. And then I also have, if I want to look at the space of invertible morphisms, that would be the derived mapping space from the nerve of this thing into x. And I have a map. Actually, I have maps both ways. I have a map like this, and that should be an equivalence. So that's one way of describing completeness. So if you keep the derived mapping space here, that's fine, but if you actually want to compute this side, then you have to find a cofibrant replacement of this and unravel what this means. Okay. Just to give you a different way of looking at that. If that doesn't say much for you, that's completely fine. It won't be necessary. All right, let's look at examples. So one, if C is a category, so I will sometimes, to stress the fact that it's just a category, I say ordinary category. Then NC satisfies the Siegel condition. If in C every isomorphism is an identity, then C is complete. just a normal nerve, the way you know it and love it, in general, it won't be a complete single space. It will be a single space, but it won't be complete. But Rask actually found a way to modify the definition of a nerve to something he calls N of C iso C. And I won't write down the definition, but if you're curious, feel free to ask. Then this is always complete. And so actually this is an instance, there's a reason there are two components here. So given a relative category, so that means C with a subcategory of weak equivalences. And there are some mild technical conditions. Then we have this relative nerve, and this is a complete Siegel space. So this was actually, for model categories, this was already shown by Rask, but then Barwick-Kahn used this to show that relative categories are a model, and then also Aaron Mazelji pushed the conditions further. Okay, and our fourth and most important example will be Bordisms as an infinity one category. So this is due to Lurie in his nice, beautiful, long paper, but this is not complete. And there's nothing we can do about it. It just isn't in general. So for low dimensions it is, but for higher dimensions it's not. And yeah, there's nothing we can do about that. Okay, great. So I told you about a lot of different models of infinity one categories. You might find that a bit unsatisfying. We have all these different definitions. But fortunately, it's not a problem. So we'll talk about this last example tomorrow in detail. And so the theorem, which sometimes is called unicity theorem, and Toen proved this for infinity one, and Barwick, Chaume-Pries for infinity n, up to an action of z mod 2z to the n, all models of infinity n categories are equivalent. Okay, so I have to add some comments here what that really means and how you could read this. So models means that we usually have a model category describing infinity one categories with a given definition. So that means we have a model category whose fibrant objects are definition we like, so quasi-categories, complete sequence spaces, or whatever. maybe we don't have a model category, but maybe we have an infinity one category. So we have a bit of an inductive definition here, right? But I mean, just as we don't want to just look at categories themselves, but the category of categories, it's the same here. We're looking at the infinity one category of infinity one categories. So to do something like this, you first have to pick somehow your ambience framework that you're working in. Right? We actually have axioms for them. So that's even better. We don't know that they're all equivalent. We actually have axioms between them. The problem is if you pick two of the models that you want, say quasi-categories and complete single spaces, you may or may not have a very simple way of going between them. So equivalence here means, equivalence here also can mean Quillen equivalent if we're a model, categories, or equivalence of infinity categories, infinity one categories. Oh, sorry, infinity one categories. Describing infinity n, here we have the n. But you may or may not have an explicit form of doing that. So the good news is that, you know, we have quasi-categories, we know what limits, co-limits are, we know what Kahn extensions are in that model. So we know how to do that in other models, in theory. In practice, then if we actually want to compute something in the other model, it might be really hard to translate. Okay. Passing through different definitions can help, or it can make things painful, right? So my advice is just pick what's useful for what you want to do, right? Yep. Yes, it's op on each level of morphisms. Yeah. Yes. So all, actually, maybe I should have put the axioms all. So there are natural axioms. So all models which satisfy this not too long list of natural axioms, they will all be equivalent. Proving that a particular model satisfies these axioms is actually not that easy. And if you want not to use the axioms but to show direct equivalences, it's also very hard. So, I mean, there are models like Verity's completional sets where at the moment, it's not connected to other models except for n equals 2, which was actually only just proven a year ago. So this is a lot of work is still to be done there. Okay, the last thing that a crash course about infinity one category should not miss is to mention the work of Emily Riehl and Dominic Verity, who are also trying to take a more axiomatic approach to the whole story to help us with this problem of like, well, we know how to do co-limits in quasi-categories, but what to do in a different model. So their approach is to formulate all these categorical constructions in a way that we can actually do it in an arbitrary model. So from now on, yep.
Can you comment on the action of z over 2z to the n?
This was just a question from the audience as well. Sorry. So this is just taking opposite morphisms at each level of k morphisms. So we have 1 morphisms, 2 morphisms, 3 morphisms to n morphisms, and on each of these levels we could take op. Okay?
Thank you.
Great. So from now on, we'll actually stick to complete Siegel spaces, just because we now want to have a concrete way of understanding the cobordism category, and, well, we want to get back to TFTs. Tomorrow we'll talk about the cobordism category and about duals and duality, and hopefully get to the cobordism hypothesis. So for that duality, again, it's not so important to actually work in the model of complete Siegel spaces anymore. We can formulate a lot of that without technicalities. But once we want to not use the cobordism hypothesis, but explicitly write down an n-dimensional fully extended TFT, we will actually need the model of complete and full Siegel spaces. So then we will get back to this. So it will be a bit of a back and forth between the two. And the only reason we're picking that one is just because it's useful for the application we want. Right? If somebody else wants to go and write down TFT, you might want to choose a different model. Then you have to find a cobordism category first. But I mean, that's, you know, there's no reason not to do that. Well, yeah. Absolutely. But if you're in for a challenge, right? Are there any other questions? Or warnings? Yes. Yes, of course. Not the way you just phrased it, though. So the way it's proven is there is a model category where the fibrant objects are quasi-categories. There's a model category where the fibrant objects are complete Siegel spaces. And then there's a zigzag of equivalent equivalences between them. From that, of course, if you have an equivalent equivalence of model categories, the model category, I said before, gives you an infinity category. So there is a way to go directly from model category to quasi-category. So from your equivalent equivalence, actually, you will get an equivalence of the quasi-categories. I don't know how to state this definition. Oh, but I was talking just now about the model category where objects in it are complete Siegel spaces. Whereas what you're talking about, I think, is to use the quasi-category for space to even formulate that. Yeah. But from that, it's not immediate how to get the quasi-category of all complete Siegel spaces. I mean, it's not hard. I mean, you can... Right, I mean, but you know, you have to deduce something. So no, none of these statements are ever trivial. There's always some steps you have to do in between. Sure. I mean, maybe if you unpack all the ingredients, right, then there are things that become easier. But I mean, just constructing the model categories here is already complicated. And from that, extracting the quasi category of these things, I mean, these ingredients are all there. You can all piece them together, right? But it's not so immediate, right? So I wouldn't say it's an obvious deduction. I mean, certainly at least there are steps. But hopefully there's this, I mean, they have to be the same, of course, yes. I mean, I'm just warning you from saying it's easy, right? Yeah, so for infinity n categories, for example, one of the axioms is that, what was the word? Gaunt n categories certainly sit inside via a sort of nerve. So gaunt means that you have strict n categories which do not have non-trivial isomorphisms. And so there are statements about this inclusion, for example, that certain push-outs of Gaunt n categories are sent to push-outs on the other side. That flavor. But there are, I mean, why do we want that? Well, these Gaunt categories, I mean, there are somehow the patterns, the basic patterns. I mean, remember yesterday I drew this picture something like this, maybe we have something like that. These are all Gantt categories. And so the idea is, well, certainly, I mean, if this is something as simple as this is a basic pattern for how to glue together morphisms, then certainly that should work in an infinity n category as well. And the push-outs that you're reflecting is basically, well, if I want to, and this will not be one of those push-outs because I don't remember exactly what they were. I think one of them is something like, if you have this type of situation, you want to be able to glue in a two-morphism. And whether you first kind of put the skeleton into the infinity n category and then glue in, or if you first glue in and then go to the infinity n category, that should commute. So they're natural in the sense that it just says something about if I paste things first and then go over to the infinity n category, it should be the same as first putting all the pieces into the infinity n category and then pasting them together. And pasting means composing morphisms. So it's a compatibility of how to compose things. So that's one of the axioms. So, I mean, fairly natural, but it takes a while to digest them. Might sound, it sounds scarier than it is. Any other questions? Okay, so to go away from the scariness of this last statement, for tomorrow, which board am I on? In the middle, okay. So for tomorrow, we'll just focus on this definition here, and actually only focus on the first part here. So, you know, if all of the other stuff confused you, just remember this definition. It's just a simplicial space, that's all. And there's this one condition here. And this should remind you, hopefully, of how a nerve looks like. So maybe, you know, it's a good exercise to actually show that a nerve satisfies this condition. So this first remark that I made, the first example, just because that's for the understanding, the crucial part. Okay. See you tomorrow. Were there still any questions left in the chat? I wasn't following. Okay, good. One second. I just want to cancel. I just wanted to stop the recording here, right?